Hi there and welcome to this video for Senior Physics on Electromagnetism and Electricity. In this video we're going to be looking at capacitors in series and parallel using the PhET simulation. Okay, so just like we had before, here is the link for the PhET simulation. So let's get started and see, let's put some of the things that we've learned into practice. So I've got loaded up here, somewhere around here. Here we go. Here is my PhET simulation. And you can see that we've got our open page. So basically what I'm doing is going to multiple capacitors here. So when I look at multiple capacitors, there's a variety of things that I can do. So first off, let's put in all our meters. We can have total capacitance, stored charge, stored energy, and I can put in my voltmeter as well. So let's start off just by looking at our voltages. So let's put up our single capacitor there. I've got it at 1.5 volts. I can measure my 1.5 volts using my voltmeter, and you can see that that's what it's reading. And then we'll check it on the capacitor, and that's also 1.5 volts. It's storing 1.12 times 10 to the 13 joules of energy, and we've got 0.1 times 10 to the negative 12 farads, which is 0.1 picofarads. Okay, now the question is, what happens when we start adding extra capacitors? So let's add an extra capacitor. Now, if you look over here, we can change the circuit by adding series, parallels, and parallels in circuits. So firstly, let's have a look at what happens when I add a second capacitor in series. Now remember, with a single capacitor, look at the total capacitance. It has actually gone down. It's gone down by a half. Now, if you remember the formula for working out the total capacitance with respect to capacitors in series, it's 1 over C total equals 1 over C1 plus 1 over C2. So it's gone down by a half, so that obeys the law. Now, what else do we know? Well, we know we've got 1.5 volts across here. So if I check my potential difference across the two capacitors, I also see that I've got 1.5. However, if I check it across the individual ones, then the result is we can see that we have changed the amount of charge and we've halved it. Now we've halved it because obviously the capacitors are the same size. So I've got 0.75 on C2, 1.5 across C1 and C2, and 0.75 across C1. So it stands to reason that when we have two components in series, they are going to share the amount of voltage which is occurring in the actual circuit. Okay, so we now know that we've got a total amount of capacitance which is halved. We know that the voltage is shared across. Now let's just go back to our single capacitor, and we can see that with a single capacitor at 1.5 volts, and remember it's 1 times 10 to the negative 3 farads, I'm storing 1.12 times 10 to the negative 13 joules of energy. But look what happens when I add more in series. You can see that the energy begins to go down. I'm actually storing less energy as I go across the three capacitors. So basically, when we've got our capacitors in series, what happens is that total capacitance decreases. The amount of voltage across each capacitor varies depending on the amount of capacitors or the size of the capacitors. Obviously, if the capacitors are the same size, then it's halved or it's a third as much across each capacitors, and they must add up to the total amount of energy which is coming out of the battery. So that basically deals with our energy, and that deals with series. So let's go back to our single. Okay, we've still got 1.5 coming through our 1.5 volts in our capacitor, and we know that we're dealing with a total capacitance of 0.1 times 10 to the negative 12 farads. So let's see what happens when we put them in parallel. So if I put one in parallel, look what happens to the capacitance. It goes up. Now remember, total capacitance across parallel is C total equals C1 plus C2 plus how many more I've got. But look at the stored energy. If I go back to my single, I've got 1.12 times 10 to the negative 13 joules, but put another one in parallel, and the result is the overall stored amount of energy increases. So this is useful if I want to deliver more energy than what the battery is actually putting out. I can use two capacitors. Now this is going to be really cool when it gets to converting AC to DC to get that nice, smooth, flat line for DC. If you remember, with a single capacitor, I was getting that ripple effect. Obviously, if I put in more capacitors in parallel, I'm going to get more energy which is going to be released, which is going to raise my line on my chart so that those peaks are leveled out. So let's put one more in and see if it still obeys the rule. Remember, it's 2.25 times 10 to the negative 13 joules here. Put another one in, I've gone up to 3.38 times 10 to the negative 13 joules. So I've got a lot more energy. Now let's also look at the amount of voltage across each of the capacitors. Remember, from our battery, we had 1.5. Yep, we still got 1.5. So let's look at C1. This is reading 1.5. Note, all the capacitors are the same. This one is reading 1.5. And this one is reading 1.5, which means all the energy as it goes through each of the branches is exactly the same. Well, this is no different to what we've learned when we looked at resistors in previous topics. Now let's see what happens if I increase the amount of capacitance that I've got in one of the capacitors. And you can see that, look at the stored energy going up. Look at the total amount of capacitance which is occurring. You can see all those charges being packed on those plates. Obviously, if I decrease it, then I'm going to come back in the opposite direction. Okay, so that deals with the parallel circuit. Let's have a quick play and see what happens if I've got a variety. I've got series and I've got in parallel. Now in parallel, let's see what we've got with respect to our voltage. Our total capacitance, remember for single, was 0.1, but with if I put it in series, I got 0.05, so I got half as much. If I put it in parallel, I got 0.2, but if I put in two in series, I've got 0.15. So I've got an in-between value, so I can start playing with the amount of energy which is going to be stored. I can also look at if we look in series, look how the stored energy goes in, but then if I put one in parallel across it, I put more energy going up. So the result is we can play around with the amount of energy by putting capacitors in either series or parallel or series and parallel. And that's going to allow us to give varying amounts of energy to our system. Let's just look at the voltage across each of the plates. Note that across the battery we've got 1.5 volts. In this case I've got 1.5 volts going through this branch. That makes sense because basically what I should have is the same energy going through this branch as going through this branch. If I look at what's going on in series, we can see I've got 0.75. So the rules still obey. I've still got the same amount of voltage going in across each areas. So let's change it and put two parallels in and one in series. So here I've got my system where I've got 1.5 coming across. So basically I should have 1.5 in each of the various branches. Now what's happened here is this is split up, so I've got 0.5. This is split up, so I've got 1.5. And this is now sitting at 1. Okay, so I've got 0.5, 0.5 and 1. Now what that means is that across the actual component, what I'm getting is 1.5 volts coming through across the whole setup. This has actually split it up as a result because we've got 0.5 here, 0.5 here. These are the same amount of energy. This is taking up one of those and these are then split into two. Okay, so basically what's left over is across the overall components, you can see I've got my 1.5 volts acting through this branch of my circuit. However, because this has been put into into parallel, it's split that up. Okay, well I hope you found that useful. That's looked at both series and parallel and applied the laws for the equations, and you can see in theory how it works. Again, go and have a play, start looking at various different types of simulations and set them up, and then try and apply them to the rules that we've looked at. Okay, well, I hope you found that useful. Thanks for watching, and look forward to you meeting me again.